Hi, I'm Dr. Julie Whitney, and I'm here today to talk to you about troubleshooting.
Troubleshooting problems has been part of human existence since the first people had problems they had to fix. This picture is a great place to start. Grace Hopper designed Harvard's Mark I computer in 1944 and is also credited with coining the term bug and debugging when she had to remove several moths from the device. You can see she taped the first one onto her engineering notebook with the comment that it was found in relay 70 on electrical panel F. Because troubleshooting is such a core part of the design cycle, as well as a core part of lots of engineering activities, people have spent time thinking about how people should be good at doing troubleshooting. At its core, troubleshooting is all about thinking logically and systematically. Your key tools are the hypothesis and the test. The hypothesis requires knowledge of the problem. It is the art of recognizing what types of problems could cause the function or lack of function you are experiencing. There are likely more than one potential cause, and maybe some are better understood than others. The key with the hypothesis is to frame your idea in such a way that the answer, once you know it, will be a yes or no. The test is then the act of answering your question. You need to find a good way to clearly get your answer. As you can imagine, thinking carefully is the key to both of these steps. My stepper motor isn't working. That's a problem, and I need to figure out what isn't working and fix it. Now, there's a lot of reasons a stepper motor might not work. The code might have errors. The Arduino might not be connected. The board that the Arduino is on may not be plugged in. It may be wired wrong. There could be a short somewhere on the board. The stepper motor could be broken. The wires could be bad. And maybe there's more things beyond that. One good way to start is to put some of the easy hypotheses first. You don't want to spend 3 weeks doing a big experiment to determine something's wrong, only to find out that you didn't plug it in. So always start with the easy stuff first. So let's start with that now. Is it plugged in? Well, there's the cord going there, and I can see up at the top the cord is plugged in to my laptop. So that's taken care of. All right. Is it connected to the Arduino? Well, let's look up here. Yes, I'm connected to the Arduino. Okay, that's not the problem. There's a light on the Arduino, so there's no shorts. Well, when I look on my Arduino, I can see that there's power getting to the Arduino board. And in fact, when I ran it, I could see that there were lights lighting up on this board, so I know that there was power getting all the way to the stepper. So, what are some more difficult things? Well, it might be the code. I can eliminate that because I was just running this code and I know that it worked fine. So the only thing that's changed is I've changed the wiring on the stepper. I had to unplug it to move it, and then I've plugged it back in again. So most likely the wiring is the problem. So now I'm focused down on the wiring and I can check that out. Let's see. I have my 5 volts and ground, and they're coming over here to this little board, and 5 volts and ground is the black, and that's on the negative, and the 5 volts is the plus. I come back over here and double check that. Yep, ground is going into the black, and 5 volts is the plus. Then I've got my wires coming over here for the motor, and they're supposed to match up with these pins over here on my board, okay? And they're supposed to go right down in order. 8, 9, let's see, red, brown, orange, yellow. And I'll come over to my board. Uh-oh, brown, red, orange, yellow. So that might be the problem. Let me swap those wires and we'll try. Well, I swapped the 2 wires and my stepper motor's moving again. So, to repeat, what did I do? I went through a list in my head of the things that were likely causing the problem. I then thought about which ones were easiest to check and checked those first. I used a little bit of logic to divide the circuit from the code, realized that my code was probably good, and then went back and checked the more difficult circuit looking at all the connections. So easy stuff first, and then try to eliminate large sections, and then get down to the thing that's causing the problem. I want to re-emphasize the divide and conquer approach. You frequently have a long list of possibilities. You get the easy things out of the way first, but once those are checked off, you can still be left with a long list, some of which will take a lot of effort to check. It's at this point that you want to rephrase your hypothesis so that answering the question, large groups of items fall under that one question, and it's possible to eliminate a whole bunch at once. With the stepper motor, our two big groups were the software and the hardware. One classic way to do that is the part swap. In a part swap, you divide the design into subsections and swap individual subsections one at a time with those from a working device. You are looking to see which subsection the problem follows. Let's do an example. This is an example of using a part swap to solve a problem. So I've got a pen here and the little button isn't working anymore. So I'd like to debug that problem. And I'm going to use another pen that is working to debug it. So I'm going to do a part swap. I'm going to try swapping parts between these two to see which part the problem follows. And I'm going to start with this end piece right here and take it off of both of them. And I'm going to put the end piece from the good pen onto the non-working pen. There we go. And it still doesn't work. And I take the end piece from the non-working pen and I put it in the working pen and it works great. So it's not the end piece. So now I'm going to take another sub-assembly, which is this centerpiece with the ink. So I will take the centerpiece with the ink out for both of them, and I'm going to put the, it's a sub-assembly, it's got a spring there. I'm going to put the centerpiece with the ink into the green pen from the non-working pen, from the red pen, and put that together. And it's broken now. And I'm going to take the centerpiece with the ink from the green working pen and put it into the red pen. And it works. So the problem followed that centerpiece with the ink. So now we look at that subassembly for the root cause of the problem. That subassembly has these two parts. That's the working set. And let's look at the non-working set. Oh, you see the problem? The spring is shorter on the broken one. Now the key to good troubleshooting, as I hope you are beginning to realize, is in the statement of the hypothesis. So what are some tools to use when you're running out of ideas as to what the root cause could be? There are a few easy tools that can be useful. The first one is to brainstorm where the problem is and where it is not. As you fill in the table, you can look for patterns that may give you a hint as to the root cause. Another tool to help you think through a problem is an Ishikawa or Fishbone Diagram. Here's an example of one made for a fictitious restaurant that's just discovered it has some problem hamburgers. The point of this diagram is to break down all the parts of the process that go into the burger, the equipment, the methods, the materials, and so forth. Each of these gets subsectioned into parts that could possibly cause the problem. Under an environment example, you have both humidity and temperature could be issues. This type of diagram helps you not overlook potential root causes, and you can formulate good hypotheses to check these. Remember, check the easy ones first and try to eliminate big blocks. MATLAB has some great debugging tools. Now they are tools, they're not things that are going to lead you to a hypothesis. They're tools for checking your hypothesis. One of them is the breakpoints tool. So you'll be selecting breakpoints on the menu. You can set or clear them. You drop the little stop signs in beside the code where you want the program to stop, and then you walk through it and see what happens to your variables. So let's go check that out in MATLAB and see how that works. Here's a nice program that I wrote, and I'm going to go up and I'm going to add breakpoints. See if I can do that here. You can't really see it. You can sort of see it set clear. And I can drop a little stop sign in wherever I want by clicking on it. Now what I'm going to do is run the program like I normally do, the little green run arrow. And it comes down and you see it stops on the very first one. It doesn't execute it. There's nothing over here. So when I tell it to step or continue, it'll go, well, I can tell it to continue, which means just run to the next stop sign. Or I can tell it to step, which means go one line of code at a time. Let's go one line of code at a time. I've told it to step. Now what it's going to do is it's going to go out and read the data right here, and it stepped down one step. You can see the little green arrow is sitting here. Now over in my workspace, I have the variable water now, this array, but it hasn't gone any further. It hasn't executed this line of code yet. So I'm going to tell it to step again. Now I have the next variable, water level. I don't have this one yet, okay? So I can continue, which will mean keep going through the program now, and it'll go all the way through and create my graph. When I want to get rid of those, I can go through my breakpoints. I can just click on them, and they'll go away. I also have up in breakpoints a thing that says clear all. So that's how you can use that debugger. But that's not the only way you can debug MATLAB. For example, I can put a display statement. So I've got my stuff over here, but let's say I want to try this again, but I'm going to just put a display in there. So I've got water level here. I can just take off the semicolon. Now when I run the program, again, it's going to read it in, and I'm going to get my, see if I can move this up a little bit so you can see it. Okay, it ran it. I get all my variables over here at the end, but I'm told exactly what water level is when it hit it. So if this was in a loop, I would get a lot of different water levels or whatever at the time, so I can see how it progressed. So that's one way to do it. Another way to do it is just to add a display or a print statement. So you can print out a value as it goes through, and you can see how that changes. So those are tools not to debug in the way of coming up with a hypothesis, but to debug in the way of testing a hypothesis to see if that's the problem.
I'd like to end the video by telling you a little bit about why troubleshooting is important. When I was in industry, I remember talking to some of the most senior technical people in our company and asking them what they thought the most important characteristic was for a good engineer. And they said the thing that defined a truly good engineer was their problem-solving skills, their ability to walk into a fuzzy, murky problem and with logic and knowledge figure out what the root cause problem was. And that's what troubleshooting and problem solving is all about.